Good morning. So today we are going to present a very interesting topic of VLSI known as Programmable Logic Arrays or PLAs. I have already mentioned in several classes earlier that the VLSI technology tries to minimize cost. Okay, that's a very important thing. When you have to develop a particular chip, for example microprocessor, okay, usually microprocessors are mostly in the initial phase, they were called custom built, so-called custom chip. You design the circuit with a lot of effort and realize the circuit on the chip from the very beginning. But in that process, I do not know whether you know or not, each microprocessor from the very beginning, the design cost was abnormally high. And ultimately the production cost, initial production cost was very high, and only if ultimately we are getting chips at a lower cost simply because that we are able to batch process the chips. We could process hundreds and thousands of chips almost simultaneously, and that ultimately cuts the cost and you get the chip at a very reasonable cost. We have already noted that with time gradually the cost of chip, you can create a per unit if you can define complexity by some in units, then the cost of chip per unit complexity is gradually going down. There are two reasons behind it. One is the processing has become very automatic, that is one thing, and second reason is that instead of using fully custom design, we are following an approach which is called semi-custom design. Semi-custom design. An example of this semi-custom design is this programmable logic arrays. So this PLAs, you can say semi-custom design approach. A good example is PLAs. Then a very important counterpart, in fact competitor to PLAs, is known as gate arrays. These are of course more versatile than PLAs. PLAs are normally meant for only certain kinds of logic implementations, whereas gate arrays are more general in nature. On the other hand, you have got some indication of such thing in the pass transistor logic, which is of course not that popular today. Pass transistor logic. Here, let us consider the pass transistor logic case. You remember the pass transistor logic can be so configured that it is an array of transistors. Only thing is you have to program it suitably. Already transistors are there on the chip. You have to connect the transistors at certain nodes only using some mask at this end stages, not in the beginning of the stages. So you can produce some master slices, which is nothing but an array of transistors configured in a suitable manner, and ultimately so chips are already processed, big wafers are already processed by some a particular set of design rules. Already it has been developed, so you don't bother about it. Ultimately, depending on your circuit need, you program it only at the last stages, maybe by etching contact holes, by designing only the metal pattern. But earlier to that, everything is prefabricated, and that ultimately leads to an extremely it's a very high cost reduction. So this is one approach. But pass transistor logic, I think you have already remembered that there is a problem, particularly gradually so many pass transistors are connected in series or in a suitably, then ultimately there is a degradation of voltage from one transistor to the next, and ultimately there is a that it suffers from the noise margin problem. So that's the one typical problem of pass transistor logic if you want to realize a very large circuit. On the other hand, PLAs, we shall see that is a very good approach to develop some usually combinational logic used for infinite state machines. For example, I want to develop a number of output functions Z1, Z2, etc., Zn in terms of a set of input variables A, B, C, D, etc. Okay, this is very often needed, and in that case, you know that PLA approach is a very excellent approach. You don't, you know, it is already prefabricated. All the thing is that you have to connect the transistors at certain node points wherever needed. So the entire design and fabrication cost is very low, and ultimately today I think you have come to know that this PLAs and all these things, whatever the programmability is called mask programmable. These are all mask programmable. That means the programmability is only in the manufacturing stage. The manufacturers can keep prefabricated slices with them, hundreds and thousands can stock with them. Then whatever order you place with them for the circuit, maybe you can send your design for the contact hole patterns and the metallization pattern. And you can send the software, you know, that the data bank for that. They will convert into masks. And these masks will be used ultimately to etch the windows, the contact holes, and ultimately to etch the metal pattern for realizing the circuit. Okay, this is what is known as mask programmable. This programmability is in the manufacturing stage. Once the chips are delivered, and if you find that suppose you have started a company manufacturing a certain kind of item for a very specialized item, and you need a very dedicated chip. So you have seen the different companies thing, and the company normally supplies you all details of whatever they have in the PLAs. So you order them that I want this kind of circuits to be implemented. You get them at a very low cost because it is a semi-custom approach. But thereafter you find that you made a mistake in your design, initial thinking. So this should not, there should be a minor change necessary. And if that minor change means the whole entire thing has to be repeated, and therefore cost will be fantastically high. So mass programmable is okay for batch manufacturing is nice, but sometimes we need repeated change in our design, particularly in the development stage, and then we need something else that I should be able to configure the circuit here in my lab, though I don't have any manufacturing facility. I don't have any manufacturing facility, but I want to configure my circuit myself. What can be done? I can use a concept which is called electrically programmable. Electrically programmable. So the other kind of things which I call electrically programmable chips. What are they? Best example today of an electrically programmable chip is, forget about memory. Memory is separate. This is called FPGAs. Field programmable gate arrays. This is GS. Or FPPLAs. Field programmable PLAs. And of course, you know, in the memory is already, you know, EEPROM. Electrically erasable programmable ROM. Here what is done is, we shall be discussing something not in detail about them afterward. We shall see that field programmable means you have some program, PLAs fabricated, prefabricated. The transistors are all there in suitable location. The array is there. Okay. Now, instead of connecting them in the mass fabrication, while manufacturing, what I do, I try to think of something which can be done in the lab. For example, let me tell you. Suppose you have made this kind of thing. Let us discuss. For example, suppose I have a metal line here. This is a metal line. Okay. It may be metal or some heavily doped semiconductor like N plus silicon or metal. All right, on which we have a polysilicon. Sorry, on which I have got a very thin oxide, very thin oxide, very thin. And on the top I have one, usually a polysilicon, doped polysilicon. This line is a conducting line, and this line, these are crossing each other. Both of them are conducting, and they are electrically isolated because there is an oxide sandwich between them. But if you apply a momentary high voltage here with respect to this, at the N plus poly gate, with respect to the N plus silicon or metal substrate, then there may be a breakdown, some kind of oxide breakdown will take place, and you will find that after the breakdown, suppose I have done it using a small pulse, a high voltage pulse, a single high voltage pulse. I have applied a fairly high voltage for a very short duration. So naturally there will be a large current flowing, but for a very short time, so there will be no overheating. There will be no overheating. So there will be no damage of the peripheral circuitry by this overheat, because I have applied the current for a very short duration. Energy dissipated is small, though the instantaneous temperature rise might be high. Okay, but this result, once the breakdown takes place, it is found that there is an irreversible change in the resistance between the N plus poly and the N plus silicon or metal. Earlier the resistance was very high because this was a very good insulator. After the breakdown, it normally gets a value around 200-300 ohms, and it is an irreversible process. Earlier this was an open circuit. After the application of the pulse, it has become practically a short circuit. So what I can do therefore, this is what is known as antifuses. What is a fuse? Fuse, normally after sending a high current, it gets blown off. So initially it was a short circuit, it becomes open circuit thereafter, after the fuse off. Okay, and this one is initially open circuit and becomes short circuit after the breakdown. So what I can do, suppose already the chip is fabricated, all the transistors are there, but I want to connect the gate of a transistor, of the particular transistor, with some line, and the drain of the particular transistor with some other line. Sources are all normally grounded, and between the line and the source, and line and the gate, I have such an antifuse. Similarly, between the other line and the drain, I have such an antifuse. What I do, I just apply instantaneous large voltage at this so-called point, antifuses, and automatically, practically a short, 200 ohms, 300 ohms is practically a short circuit to a MOSFET. MOSFETs are, normally very high resistance devices. So 200, 300 is practically a short circuit. So you can create the nodes in your lab. I want to create a node, a connection, and that I can do in the lab. The other alternative, this is very good. This is, of course, once it is done, you cannot reuse it. Suppose I have configured the circuit by this approach, but thereafter, if I want to reuse it, reprogram it, not reuse, reprogram it, it is not possible because it is an irreversible process. But in electronics, again, we want reprogrammability. That is the characteristic of EPROM, electrically erasable programmable ROM. I can program, I can erase also. Here also you may need that. In that case, can you tell me what you can do? Suppose I want that between the point A and B, there should be either an open circuit or a short circuit. What I can do? I can do it electrically. Using suppose you want your circuit to work only when the power is on, known as volatile condition, volatile memory. Theoretically, you can connect the output of a latch or a RAM between this. Here you can connect the Q, and here you can connect Q bar, output and output complement. When the switch is preset, then this Q is 0 means this voltage is 0. Voltage is 0 means practically short circuit. Is all right? Suppose I program the particular memory element which is connected between the two nodes. I program it to be 0, that means the output is preset to 0. Then AB points will be short circuited. Node is established. And if I reset it, this is open circuit. This can be done by making use of a RAM, normal RAM, with a battery backup. So in that case, it is very inexpensive. RAM with a battery backup is equivalent to, practically is equivalent to a ROM. You can program it and keep it. So long as the battery life is okay, it is programmable, can keep it. So RAM with a battery backup if you use, then you know the RAM can be formed in a relatively high density. So high density means not as compared to dynamic RAM. Dynamic RAM cannot be used here. Dynamic RAM cannot be used here. You have to use RAM. Some memory element, static memory, a latch up, nothing but a latch circuit. And these two can be short circuited or open circuited depending on your instruction. This is called a field programmable gate arrays which can be reprogrammed. In our department, I think we have got one facility in the digital communication laboratory and one facility in that, I think it is there in the CAD VLSI lab. Whether it has come or not, I do not know, but this is coming. And here, a student can design his own circuit. Design and fabricate his own circuit, so though he does not have a foundry. You don't have a foundry. That's a problem of our VLSI CAD lab is, it is a little bit demoralizing sometimes. You do your entire work and you design, but ultimately fabrication is not possible simply because this fabrication is tagged with some foundries in USA. Because you know that we have got VTI tool, VLSI Technology CAD tools. It's an American company. They have tagged with certain big foundries in USA, Japan, and Singapore, and those. They are very expensive. You can design because all the design tools are available. You can design it. But ultimately, fabrication is not possible, has not been possible using the VTA so far, simply because of the exorbitant cost wanted by these companies. Only some local efforts were made. ITI has got a foundry, and using ITI software, we developed something which was ultimately, realized, and they are not that high density. If you want a very modern VLSI chip, you can design it here, but you cannot fabricate simply because of that limitation. It's very expensive. But using this facility, you can do it. You can use the VLSI CAD tools, whatever available in the CAD VLSI lab, and they are normally interfaceable with the FPGA software. FPGA normally they provide a software so that you can you cannot do it by hand one after another like this. You have to do it by computer-aided means. Okay, that kind of software is available, and you can realize your circuit yourself. And remember, it is a VLSI circuit. And you remember that in this case, the cost-wise, of course, for this FPGA's cost-wise advantage is not there. Please remember, because it is a dedicated chip only for 5-6 applications, and thereafter, ultimately, what is done is, if by FPGA we design something, realize it, and afterward you get satisfied with your design, then what you do? You now ask the company to make normal gate arrays, mass programmable gate arrays in large numbers. So it becomes very inexpensive. Okay, so that's the approach. Let us now try to concentrate to PLAs, which is the topic of our discussion today and for the some classes from today. Say, let us consider three functions. Z1 is AB plus A bar B bar C. Z2 is equal to AB, and Z3 is equal to A plus B bar C. So there are three functions and three variables. You see that there are three output functions, Z1, Z2, Z3, and three variables A, B, and C, and their complements. Okay? And I want to realize this Z1, Z2, Z3 using an approach which is called field programmable gate array. Sorry, this is called not field programmable, simple programmable logic arrays. So what I do, you know that any function can be represented as a sum of product. That's a general sum of products. Each product, again, from the realization point of view, particularly for MOS realization point of view, each product, it is better to realize using NOR gates rather than AND gates, because you know the AND gate has got the problem of stacking. You have to use larger ratios of the drivers. For AND gate or NAND gate realization, you have to stack the driver transistors. Instead of that, it is better to use NOR gates or OR gates where the transistors are connected in parallel, and therefore no question of higher ratio, W by L ratio. That is very important. So what I do, I express AB therefore as A bar, B bar as a NOR gate. Similarly, A bar, B bar, C as A plus B plus C bar, and ultimately the other variable whatever available is B bar C is equal to B plus C bar. These are all NOR gates which can be easily configured in MOS technology. So MOS is naturally NOT type, nor NAND type. You remember TTL is naturally NAND type, whereas MOS, ECL, etc., they are naturally NOR type. Please remember this. So what I do now, simply so I first produce from the input variables their complements also, A and A bar, B and B bar, C and C bar. Okay, the standard way. Then I have to produce the product terms. There are how many product terms? AB, A bar, B bar, C, B bar, C, and A. So there are 4 independent product terms. A is not product but a single, but there are 4 terms to be realized. And therefore, what I do in the normal structural logic approach, I use 4 NOR gate, because NOR is natural, as I told you, in MOS. I want to produce at the output the following terms. One is AB, the other is A bar, B bar, C, third is B bar, C, and finally A, to produce the 4 functions. So naturally I have to connect at the input as indicated here for AB, A bar, B bar, for A bar, B bar, C, A, B, C bar, B bar, C, B, C bar, and A bar. Sorry, A bar. So please see that all these A bar, B bar, A, B, C, etc., these are all produced in this particular stage. I have to simply connect them. Already I have produced the variables and their complements, and they have to be connected at the input to produce these so-called terms or product terms. These are the product terms. And ultimately, I have to combine them to produce Z1, Z2, Z3. As I told you, NOR is natural, therefore I will first make the NOR functions out of them, and then another inversion stage to produce the final function. NOR, invert is OR. So what I do, therefore I take, because there are 3 output functions, I have to take 3 NOR gates. I want to produce Z1 bar here, Z2 bar here, and Z3 bar here, so that after the inverter I get here Z1, after the inverter I get here Z2, after the inverter I get here Z3. Alright? And then you simply connect, because this Z1 is nothing but AB plus, therefore what you do, you connect this one here and this one. You get this one. Z2 is nothing but simply AB bar. So you just, Z2 is equal to AB. So you just take something from here. This is nothing but a simple, this is simple, basically an inverter. And then ultimately to produce this function, you get, this is I have written A. Yeah. So you see that basically in the first stage I have an inverter. I have a column of inverters, then a column of NOR gates, then column of another column of NOR gate, and finally again invert. The purpose of the whole thing here is to produce AND functions. Normally I will call it, I shall say in the nomenclature of PLAs, AND plane. You just ultimately you produce the AND functions from the input variables. So whole thing, the inverter, the column of inverters and the column of NOR gates, which are natural. This inverter is natural, is very natural in MOS technology, and NOR gates are also very natural in MOS technology, and therefore you know that you can, by combining them, you have produced AND functions here. So this is normally called AND plane in the language of PLAs. Whereas from here, ultimately you are getting ORing them. That's what are doing through 2 stages. One is NOR, the next is invert. So I will call the next stage is OR. Now, so far as block schematically, you see that this appears to be a little bit complicated. The way we have drawn it, it appears to be a little bit complicated. But when you come to the actual life, actual practice, you will find the realization of this is rather simple, and that is why PLA is so popular. The whole thing, now we have just given an example, a very simple example, only 3 output functions, only 3 input variables. In actual practice, it may be 64 input variables and 64 output functions. It's a much more complicated thing. And if I want to really think in this kind of thing, the way I have drawn the block schematic, it ultimately appears to be rather complicated. But we shall see just now that from this basic block, I can create the PLA, which is very simple so far as VLSI implementation is concerned. Consider now the case of the same thing to be realized by a regular PLA structure. Regular, we shall see that PLAs can be divided as regular PLAs and folded PLAs. We shall see that PLAs can be folded and compacted. But whatever I am now discussing, they are simple regular PLAs without any compaction. What I do, I simply have 4 rows like this. And connect at this stage So I'm not really drawing any stick diagram, simple wire diagram, simple wire diagram. You see that I want to produce now at the 4 output. These are the 4 out. These are called product lines. These rows will be called product lines. So what I will do, I will produce the following functions here. Here I will produce A. Here I will produce my B bar C. Here I will produce A bar, B bar, C, and at this point I will produce the last function, which is the way I have prepared is like this. You could, there is no, the ordering is arbitrary. You can keep any order. So these are the 4 product terms I have to produce. A, product term is though it is A multiplied by 1. So A, B bar C, A bar B bar C, and AB. These are the 4 independent product terms involved for realizing the 3 functions Z1, Z2, Z3 as sum of products. What I do now simply to produce A, what I do? I have to invert, because already you know that I have A. I should not connect it like this, because it cannot be connected because there is always. Please remember, below each point there is a transistor. Below each intersection there is a MOSFET. But these are isolated. Please remember, I have developed in such a way there is an array of transistors. How many transistors are there? 6 into 4. 24 MOSFETs, N MOSFETs. These are all driver transistors. These are load transistors. These are load. 6 into 4, 24 driver transistors located below these points. Only thing is I have to use suitable masks to interconnect them. For example, I want to produce A. What I do? I simply between this point A bar, I connect a transistor like this. You just see that this is nothing but an inverter. This is a load transistor of the inverter, and this is a driver transistor of the inverter. So at this point, I have connected the transistor in such a way that the row line is connected with the drain of this transistor, and the column, so-called input line, is connected to the particular A. This is here we are producing A inverse. So A inverse at the input produces A. Similarly, I want to produce B bar C. What I do? I connect a transistor here. Sorry. It is equivalent to producing, you have to apply B at the input and C bar at the input to produce B bar C. Exactly that. I have applied B at the input. So this is nothing but a NOR gate, and you have connected B at the input of this driver transistor and C bar at the input of this driver transistor, which are in parallel. Both of them are in parallel. Similarly, A bar, B bar, C, how to do for this line? I have to connect and for AB, what I have to do? Over. So I have produced the 4 product terms. I have produced the 4 product terms by this process. I am again reminding you that already the transistors are existing. Only at the latter stage of fabrication, for etching holes and metallization, you connect them. Otherwise, it is existing. So fabrication, it is very simple. Even design-wise, also it is very simple. But design-wise, we shall see that for each, you know, that you have to, that we shall discuss after. Then ultimately, I have to NOR them first and invert them second to produce my function. So again, I have to now, I extend the 4 lines. So I want to have the function, sorry, Z1, Z2, and Z3 at the 3 output points as indicated. So what I have to do? I have to NOR them suitably and then invert as indicated. For example, I have to first produce Z1, which is AB plus A bar B bar C. So what I do? I take AB and A bar B bar C at the input. You know that this is the now the load transistor of the corresponding inverters. And then what I have to do now, only thing I have to connect them in a little bit different fashion like this. Produce Z1. You just see here I have connected A bar, B bar, C at this gate and at this gate AB. So the NOR, you get the NOR of them here, and after inversion you get Z1. Similarly Z2 is AB, simply AB. What do? You take the AB and connect here. This is simple plain inverter. And what is Z3? Z3 is A plus B bar C. Simply you connect here. And the whole thing here, from here to here, will be called AND plane. And the whole thing here will be called OR plane. If you look, you examine the AND plane and OR plane carefully, you will find they are identical. They are the same thing. Only thing is connected in the, you know that here you can say the rows and columns have been interchanged as I go from AND plane to OR plane. Structurally they are the same. You see that inputs here have been connected to the columns. Here the inputs have been connected to the rows. Here the outputs were taken from the rows and the outputs in this case have been taken from the columns. So basically structurally both AND plane and OR plane they are identical. They are identical. Only thing is there, you know that you see that here there are additional inverters, that is not there, but otherwise they are the same. Now the problem is that you see that this appears to be very simple, but when you try to think, when you are thinking of realizing in the VLSI form, one problem will be automatically coming, that is the invisible ground lines. You know that whatever lines and rows and columns, whatever I have shown here, the rows represent here nothing but the output lines of these inverters, and columns nothing but the input lines of these inverters. But inverter has got what are the minimum points necessary in inverter? One is the VDD supply, the other is ground, these are important. Then inputs and outputs. You see that inputs are visible, outputs are visible, VDD is also visible, but ground is visible only locally. Only here I have shown, because the transistors have been indicated only local region. I said the transistors are there. Only thing is these transistors are not connected here, etc. All these nodes, transistors are not connected. Only at these specified nodes, the transistors are connected. Inputs and outputs are properly connected. So you have to think of how to lay the ground lines. Let us see an example. Same thing realized on a chip. And that will be shown by using, you know, the stick diagram approach, that is more convenient. So this is the, you see that I am showing only the AND plane, not the OR plane. AND plane of the same PLA which I just discussed. Here you see that the stick diagram has been used only for representing the rows and columns, but these transistors here and the inverter, they have been kept out of stick diagram. You know, this I have not drawn in the conventional stick diagram, but you could draw it. You can just extend like this. Now, how to connect the transistor? You see that we have 4 metal lines, which I am calling rows. 1, 2, 3, 4, 5, 6 poly lines, which are input lines, and 1, 2, 3 ground lines. And as per rule, you remember that if a poly crosses a metal, there is no connection. Similarly, this is also the ground lines are, you know that this is I have shown it by using diffusion. A single solid line means diffusion, double line means metal, and dashed line means poly. I am using one color representation of the stick diagram. Therefore, these are nothing but diffusion lines, N plus diffusion lines. Please remember, these 3 diffusion lines which are grounded. So at the intersection of the different lines, no connection exists as per the laws, as per the rules which are framed while drawing the stick diagram. Now to connect the transistors, first let me produce this function. So let us start with A. What is to be done? For producing A, what is to be done? I have to have a transistor here. A bar has to be inverted to get A. So I have to have a transistor here. So what has to be done for this? Simply I do the following. At the intersection of the metal, of the poly and diffusion, there is a transistor as per rule. So this is nothing but the extension of the diffusion, this branching of diffusion. It crosses the poly level, means there is a transistor here, and then it crosses this with a cross cut. That means there is a connection between the metal and this, and you get A here. To produce B bar C, what I have to do? Between B, so what I have to do is simply I can take this one and this one, and B bar C. C, if it's C bar means simply I have to do A bar, B bar, C. A bar means this one, A. So I have to do the following. And finally B bar C, that means BC. It is AB. This is AB, right? So how to produce AB? A and B. AB means this one. AB. So what we have obtained is that you have to have really the hidden ground points, which is shown here. There must be some power line, like just VDD line. There must be, in this case, a distributed ground line in the substrate. The ground line must be distributed properly and ultimately connected. Stick diagram is an easy approach of showing the layout. That is why we have drawn it through stick diagram. So this way you can really implement the end. So I think now I'll stop for a few minutes and go for the second part. Thank you.